Okay, welcome to class. The Friday before a long weekend. I'm flattered you actually came. That's fantastic. Thanks for being here. Today we're going to finish chapter 16 and that's it. So we probably won't finish early, but we will finish the content early and then just do a bunch of example problems, which I think is going to be helpful for the homework. So our learning objectives are, first off, we're going to just slightly modify what we learned last time by doing an example where the number of electrons exchanged are not equal, right? I'll show you what I mean in just a moment. And then the last thing we have to cover in this chapter before we move on is oxide growth, and how do you actually predict what type of oxide will grow? Will it look like Swiss cheese, or will it be completely dense? Will it chip off? Will it not? We have a way to sort of estimate that works pretty well. Now, a quick announcement. Homework 1 is already graded. I'll be posting the solution a little bit later tonight. Homework 2 I posted on Wednesday, so if you haven't seen that, it's in the files section on Canvas. You can grab homework 2 already. You want to get started on it. Now remember, your grade on Canvas for homework 1, maybe you got a 10 out of 10 on it. I still recommend you coming to my office and picking up your homework. We're not allowed to pass them back in class. They've cracked down on that. It's actually illegal for me to pass them out in class. So instead, you have to come get them from me or from the TAs. I do suggest you picking it up because we only grade half the questions for accuracy. The other ones are for completeness. So you might have actually done the question wrong, but it was one that we graded for completeness. So you definitely want to look at the solutions, and I recommend picking up your homework and making sure that you did it right. Now, Monday's a holiday. Monday's Labor Day, so we're going to miss the TA hours, which were on Monday, and there was 4 hours that day. So a student asked if we could move those. So let's have that be our first question for today. No right answer. This is just participation, obviously. But I'd like to hear your guys' opinion. Since Monday's Labor Day, Danny's offered to do extra T hours, hers which are normally on Monday. She's going to do them on Tuesday. Would you rather have them 7 a.m. to 9 a.m.? It's early, I understand, but she has classes. From 12 to 2, or would you rather have 2 TAs present for the evening session from 5 to 7? So go ahead and get your answer in. This is worth a point for just participation. Okay, everybody got their answers in? 8 people do not. What will it be? It's going to be an even split. Okay, I'm going to wrap up the poll. Okay, people want what? They would rather have 2 TAs. Okay, so that said, are you going to do them both in this room? So still come to this room on Tuesday night, and we'll just have 2 TAs, so hopefully we can get through more of your questions, or at least have more. If someone's stuck, maybe the other TA can move on while the other TA helps out the individuals. And I'll ask if Logan can do one of the other 2 times, for example, 12 to 2. I'll see if he's available for that, but watch for an announcement, because right now it's not guaranteed. Yeah, question? If you can't make it to the TA hours, let's say of all the 5 or 6 different times we have during the week for TA hours, if you can't make those, I suggest using Canvas. The discussion section on Canvas is a great way. You just post it, say, homework 2, problem 2, 3, whatever. Like, anybody else having issues with this? Like, how do you get started on this problem? I monitor those really closely. The TAs do as well. So if you can't make it to office hours, those work really well. Anytime my door's open, which is half the hours in a day, you can pop in my office and I will always make time to chat with you. So those are other options. Okay, where we left off last time, we did an example. We did it for zinc and for iron. And if you look at our table, our standard reduction potential table, both of these ions are 2+ when they start, right? Zinc is zinc 2+, and iron up here is also 2+. So when we figure out which one's going to get flipped, and the one that gets flipped is the one that when you reverse its sign and you add it up, you get the largest positive number. So that's going to be the one that's lower on the table, the more negative one. Okay? That allows us to write a overall redox reaction which has both the oxidation and reduction. And you notice this 2 electrons, we canceled it out because it's the same, right? 2 electrons on both sides, people just don't even write them. But what if we'd chosen something other than 2 plus, right? And then you've got 3 electrons, you've got 1 electrons, or 4. Then we have to modify this, and let's do an example of that, right? So let's do one. Let's do, say, silver. Silver's at the top up here. Silver 1 plus picks up 1 electron to form silver metal. Let's do that with, I don't know, like iron. That one's tricky. Let's do chromium 3 plus. Okay? So let's write that one down. We've got one where it's n equals 1, one where it's n equals 3. So we're going to say silver plus picks up 1 electron to form silver metal. Meanwhile, chromium 3 plus has to pick up 3 electrons to form chromium metal. This has a voltage associated with it. It is, silver is 0.8 and chromium is negative 7.44. So right off the bat, we could ask you which one is going to get flipped. So tell your neighbor which one gets flipped and why do you know that? Okay, let me ask Reagan. Reagan, can you explain which one gets flipped and how do we know?
It would be the chromium because it has the larger negative voltage.
That's just the rule. The one that's more negative gets flipped. Now, why is that the case? Why can we say the one that's more negative? Is there a reason for this that makes sense? Yeah.
Because it's more reactive.
For one thing, it's more reactive. The things at the bottom of the table are more reactive, meaning they're going to want to get flipped, whereas the ones at the top are inert. There's a reason that we make rings out of gold, because gold's relatively inert. It doesn't corrode easily, right? Silver, platinum, these, in fact, we call them the noble metals, right? Because they don't corrode very easily. They can corrode, they just don't easily, right? Another way to think of this is, okay, we've got these two things. Right now, if we add these up, we don't have a redox reaction because they're both reductions, right? We need a redox, so reduction and oxidation. So when we flip this, we get chromium goes to chromium 3 plus ions. It dissolves by surrendering 3 electrons. That allows us to change our voltage to now positive 0.744 volts. And when we add these two together, we add, this is going to become VR for reduction. This is V oxidation, O for oxidation. What's called the standard reduction, or sorry, the overall cell potential, excuse me. Delta V naught is the overall cell potential. Let me just write it down. Overall cell potential. That's equal to VR plus VO. And we want that to add up to the largest positive number possible. The reason why is because unlike free energy, where a negative delta G for a reaction is spontaneous, by convention, a positive voltage is spontaneous. And when we add these things up, 0.8, so this is going to be 1.544, right? Our voltage, our overall cell potential, is equal to positive 1.544, oh gosh, 1.544 volts, okay? Now, we remember from last time that just like free energy, there's two parts to any electrochemistry. What we just solved was the theoretical part, right? So if we go back to our expression from last time, we said this delta V naught, that's what's called the overall cell potential. That doesn't give you the whole picture. In fact, the name's unfortunate because overall sounds like it's like the final one. Instead, we want the cell potential. Sorry, I didn't make up these names. I would have done it differently. But the cell potential takes into account the theory, overall cell potential, plus all of this, which has to do with what's actually present in your battery, right? Like, I could say that the battery in your phone is supposed to work on paper. You know, lithium goes from one side to the other. There's a thermodynamic driving force. But if your battery is depleted and these ratios have changed, then your battery may not actually operate like you expect. So this takes into account the actual concentrations of your oxidized and reduced species, and that becomes really important. Okay? Any questions so far? Okay, let's keep going. By the way that we can relate free energy to voltage. We said this quickly last time, so let's just emphasize it. If you had a delta G for a reaction, you could actually imagine what voltage would be associated with that reaction if it was carried out electrochemically by just taking negative N, the number of electrons involved in the reaction, multiplied by F, Faraday's constant, right, times your delta V, your overall cell potential. That will equal your change in free energy. So you can convert between the two, okay? Now let's get back to our example. We have silver and we have chrome, and we decided that we can add these up. But when we add them up, watch what happens. I've got chromium plus silver ions plus 1 electron is giving me chromium 3 plus ions plus silver metal plus 3 electrons. So there's a problem here. Our electrons are not balanced, right? So we have to modify this. We're going to do that by modifying the silver equation. We're going to say everything here, we're going to multiply it by 3, because then we end up with 3 electrons. So that means that we're going to have, instead of just 1 silver ion down here, it's going to be plus 3 silver ions. And instead of just 1 silver metal mole being produced, it's going to be 3, and that puts 3 electrons here. Let me just rewrite that. Make sense? We did that because silver only had 1 electron and chromium had 3. So when we added together, first off, let me get rid of this equation. That's the one that we flipped. When we add those two equations together, there was an unequal number of electrons, so the equation wasn't balanced. It looked like it was balanced, but it wasn't balanced because the electrons weren't. Okay? Now, critically, this is really critical, we did not multiply this by 3. Do not times by 3. Okay? That is the difference between electrochemistry and free energy. In free energy, right, if this was enthalpy or Gibbs energy or entropy, we would have multiplied that number by 3 or 2 or whatever the number was that we multiplied the equation by. You do not do that for electrochemistry. That's the big catch to remember, okay? Okay, so now we have a balanced chemical equation. We could go ahead and solve for the now cell potential, not the overall cell potential. We could actually measure the voltage that this battery created as follows. We'd say delta V equals delta V naught, which is this guy. Okay? Plus, or now it's minus RT over NF multiplied by the natural log of our, again, it's going to be products over reactants. So our product is chromium ion. So it's going to be chromium 3 plus raised to the 1 power, because it's only a coefficient of 1. That's going to be divided by the concentration of our silver ions. And those are going to be raised to a cubed, right? It's exponent of 3 because there were 3 in the coefficient for silver. Everybody catch that? It's just like reaction products with like the partial pressure of gases, where the coefficient became an exponent. It's the exact same thing here. Okay? Any questions? So for this reaction, I could give you the concentrations of chromium and silver, and you could figure out what the actual observed voltage is. If you hooked a multimeter up to this thing, you could measure that voltage. Again, this only tells you on paper what it should be close to. The experimental conditions will change it. Now, what do you do for N? N is the number of electrons. That's the balanced number of electrons. So this needs to be 3. Okay? Let's say that you wrote an equation that instead of being a mixture of 1 and 3, it was 2 and 3. Maybe you did like zinc 2 plus with 2 electrons. Then you're going to have to multiply both of these, 1 by 3, 1 by 2, such that your overall number of electrons is 6 to get it balanced. In that case, N would be 6. Any questions on this approach, how we do this? We're going to do some actual, we'll do more calculations in a minute. Okay, and there's more on YouTube if you want to, obviously, like all these things. Okay, that said, let me shift gears just a little bit before we do a bunch of example questions and ask this question. If you take a metal and you take it out of an aqueous environment, and we all know that a boat, if you leave it in the ocean, is going to corrode. Or if you leave iron in the rain, like if you have a bicycle and you leave it out in the rain, it's going to corrode. It's going to get rusty, right? The question is, if you take it out of water, do you guarantee that it stops corrosion? Or in other words, is water a necessary condition for corrosion? Okay, we're going to wrap this up. Get your answers in. Okay, we're going to close the poll. If you take it out of the water, does corrosion stop? Definitely not. Hopefully, like this isn't, like you've seen this, that things can rust or tarnish even if there's no water around, okay? Okay, so yeah, you see this, right? Take your grandma's silver spoon, right? There's a reason she has you like polishing those things, because tarnish can form just from its reaction with air. Actually, tarnish is sulfur. That's a sulfidation, I think, not an oxidation reaction, but still, it's what's present in air that it reacts with. So the general reaction for oxidation is you take a metal, add some oxygen to it, depending on the oxidation state, how much oxygen, and you form a metal oxide, right? So in that case, we could actually split that into the oxidation and reduction half-cell reactions, right? If you have your metal, it starts out a metal, it's going to turn into M2 plus 2 electrons. It gave up electrons to do so, so it was oxidized. Meanwhile, you can have a half of an oxygen molecule. That's going to pick up 2 electrons to form oxygen 2 minus, right? So you've got so it's still a redox reaction. You have your half cells of both types, okay? But think about what this means for this to actually happen. Since these are not in the gas phase, the oxide, then this is what happens. You've got your metal here, and you've got oxygen out here floating around. But as it reacts with it, you're going to form a metal oxide layer, okay? So this means that you still have to have a way for your oxygen, which is out here, to react with your metal, which is over there. Otherwise, your corrosion stops. So this is critical. This means that in order for corrosion to continue, one of two things has to happen. You either have to have oxygen diffusing in, right? Oxygen 2 minus or oxygen gas, if this is a permeable layer that gas can get through. It has to travel inward, or your metal ions have to travel outward. One of those two things has to happen in order for corrosion to continue, okay? And that's not always the case. Some oxides don't allow that. They form what's called a passivating oxide layer, right? Aluminum is a great example of this, right? Aluminum, actually this is anodized aluminum. Who's got one of the new iPhones that's like a funky color? Anybody have one? Surely someone has a funky colored iPhone, right? The reason they can get it funky colored is because it's actually an oxide layer. They call it anodized alumina. Anodized, what does that mean? That it was an anode. What did they do to the alumina? Anodized. They oxidized it. It went from being aluminum metal to aluminum. Losing electrons is something like aluminum 3 plus. So that's the oxide. They formed an oxide on purpose. And the reason they do that is because the oxide layer is harder, so it's more scratch resistant. And we're talking thin, real thin layers. But it's a little bit porous, and they can put dye molecules in the spots between the aluminum oxide, and so you can dye it. You can turn these things funky colors, okay? Regular aluminum, even unanodized, is oxidation resistant. Like there's aluminum in this room surely somewhere. Like this is probably aluminum, right? And it's not rusting, and it won't rust. And the reason it won't rust is because it rusted already, if you will, right? We don't call it rust. It formed an oxide already, and that oxide is just super, super impermeable to either more metal traveling across it or oxygen traveling across it. So it's blocked. So you have your reactants and products are separated. So your oxidation stops. And this happens really quickly. If you take, what do you call it? The stuff that you scrape off rust with. Brillo pad. A Brillo pad would do it. If you took Brillo pad to aluminum or steel wool. If you took steel wool to it, you'll remove it temporarily, but it's going to grow back very, very quickly, right? And that's just aluminum. But aluminum's kind of atypical in the sense that it forms a passivating oxide. Many other metals don't form a passivating oxide, meaning once it grows an oxide, it can just keep on growing. And that can be to a couple reasons. It might be that this oxide layer grows to a certain point and then it just chips off. Anybody who's touched like rust before and seen how it just chips off in your hands, that's why rust keeps on corroding. And in other cases, it grows kind of like Swiss cheese. There's big passages through it because it's not totally dense, and that allows oxygen to reach this surface, and it can grow inward, okay? Any questions on this, on the concept of oxidation? So how do we know which one is it going to be? Will it passivate? Will it grow? Will it not grow? Will it have Swiss cheese? We have a really great ratio we can use. It's called the Pilling-Bedworth ratio. The Pilling-Bedworth ratio, it's clever that this actually works. All they did is they said, okay, we've got this scenario where you've got a metal and it's going to turn into a metal oxide. They ask this simple question: is the volume equal? Right? So in other words, for every 1 mole of metal that I corrode, do I create 1 mole of oxide that has the same volume? Right? If it's the exact same volume or close to it, then it's going to be a nice fit, and it's just going to keep on growing. That's like what happens with alumina. It's a pretty much very similar volume. Okay? But if you grow from 1 mole of metal, if you grow 1 mole of oxide and it's a lot bigger in volume because of the way that the atoms arrange themselves, which we'll learn in a couple chaptits, then all of a sudden this thing's really big. Like imagine it's going to be experiencing like a compressive force like that. If it's trying to expand but its substrate that it's growing on doesn't let it, then it's wanting to expand and it's eventually going to chip off, right? That's what happens with rust. It chips off, like iron oxide rust. And then imagine the other way. Let's say that the volume of oxide is actually more condensed, which is sometimes the case. It's a smaller volume. Then to make up for this, it's going to have holes in it. It'll have Swiss cheese holes all through it, right? So all we need is a way to compare the volume of the metal to the volume of the oxide. And that's what the Pilling-Bedworth ratio does, right? The volume of the oxide to the volume of the metal is just equal to the molecular weight of the oxide, that's capital M, multiplied by the density of the metal. Notice that the oxide and the metal are switched here, right? You've got oxide, metal, metal, oxide. So don't write that down wrong. That's going to be divided by N, the number of metal atoms in the metal oxide, and the molecular weight of the metal, the density of the oxide, okay? So what do I mean by N? Let's say you have vanadium metal. Well, if the oxide is V2O5, then there's 2 vanadium atoms in the oxide, right? That's what N is there. Okay? So we said if the Pilling-Bedworth ratio is less than 1, then we get, I'm pretty sure this is the case that it is, let's see, well we can figure it out. If the ratio is less than 1, then that means that the volume of the metal is less than the volume of the oxide, so you're going to get spallation, is that right? Is it the other way around? So how about this? So let's just write it out. If the Pilling-Bedworth ratio is greater than 1, then 1's here. Pilling-Bedworth ratio is greater than 1, then V metal is greater than V, sorry, I have that backwards. Replace that one up top. Your oxide ratio is greater than your metal. So when you bring metal over, yeah, the metal is larger than your oxide, therefore you're going to get Swiss cheese. Okay? So this is Swiss cheese. Swiss cheese. Am I backwards? Am I right? I think I'm right. I will consult the book tonight and make sure this was correct. I think that's right, though. Swiss cheese, or in other words, you get porosity, right? If you have porosity, that means you have a pathway for oxygen to get to the surface. It's going to keep on corroding. If it's equal to 1, then it's going to be passive. If it's greater than 1, then you can get, we'll call this one spallation for sure, if it's like greater than 2 or 3. If it's between 1 and 2, it might be stable, right? Okay? You can sometimes observe how the oxide is growing by monitoring the weight of this. So there's tools to do this. You can actually take a little tiny pan, put your sample inside of there. You can heat it up to a temperature, and you can monitor the weight of that pan over time, right? Assuming that there's oxygen for it to react with. And there's different scenarios, right? If your weight gain is parabolic, right? So you've got your weight gain, weight versus time. If it's linear versus parabolic versus linear or logarithmic, these represent different growth rates, right? Linear means that you have either Swiss cheese or spallation, right? Because you have an easy path that when it corrodes, it can just keep on corroding. So that's going to be linear growth, right? Spallation or porous oxide when it's linear. If it's parabolic, then you are starting to form a passivating layer. And logarithmic is for thin films. We're not going to talk about that. Okay, any questions on oxidation? That's all I'm going to say about that in this chapter before we do some examples. Any questions on it? Pilling-Bedworth ratio, electrochemistry. Okay, we got 25 minutes. Let's do a couple example problems. Okay, how about this first one? 2 moles of SO2 as a gas is going to react with oxygen to form 2 moles of SO3. Okay? If I told you in this question on a homework or on a test that the equilibrium constant K is equal to 10 at 960 Kelvin, I could ask you to calculate delta RG and indicate the direction of spontaneous reaction, assuming that these were our initial partial pressures. Okay? So this is our next clicker question, I think. So yeah, you're actually going to put your answer in kilojoules per mole. Okay? So I've given you the equilibrium constant K. What is K? K is a special word for Q, our reaction quotient, at equilibrium. Right? At equilibrium, K is equal to Q. If it's not at equilibrium, you just use Q. Okay? So I told you that K is 10 at that temperature, and I've given you the partial pressures, and I'm asking you to solve for delta G for this reaction. Delta RG. The change in Gibbs free energy for the reaction. Let me just help you get started on this one because it's a little bit tricky. Remember, normally we need this. We say that delta RG is equal to delta RG naught plus RT natural log of Q. Okay? Now I've said that at equilibrium, Q is equal to K, and in this problem, not every problem, in this problem, that's equal to 10. We also know what at equilibrium? What else do we know at equilibrium? Delta RG is 0. That's critical. Delta RG equals 0. So I've given you this information, and then I've said, okay, no longer at equilibrium, but if these are the starting things you have, what will be the direction of the reaction, right? What is delta RG? So what I haven't told you is this. I haven't told you this value, right? But you can use the equilibrium information to solve for delta RG naught. And then under non-equilibrium conditions, when you plug in for Q, you can figure out delta RG. Okay, so give that a shot. If you're stuck, we've got at least 2 TAs here, and they're happy to help you out. I'm going to help. Are you assuming what now? Sorry, one more time. Yeah, Kelvin. So no, at 960K. Yeah. The temperature is 960 Kelvin, and the gas constant I'll write down. Anybody stuck? Need help? What's up?
So I didn't follow what you mean about how we're gonna like.
Okay, so I haven't given you delta RG naught, but normally if you need to solve for delta RG, which you have to, you need to have the reaction quotient Q, right? So Q is going to be what, right? How do you solve for Q?
Well, I thought you said Q was gonna.
That's only at equilibrium. The second part of the question is not at equilibrium. So you can't say, this just has to be Q, not 10 there. So what is Q normally equal to? So it's products over reactants, and these are all gases, so you can write the partial pressure of those things raised to their exponents. So your product is SO3, so it's going to be the partial pressure of SO3. and that's going to be squared, right? Because there's 2 moles of it.
Yes.
That's going to be divided by your reactant, so the partial pressure of oxygen to the 1 power, multiplied by the partial pressure of SO2 squared. That is Q. That's what goes inside the natural log function. Okay? Once you do that, that's going to allow you to say this is at not equilibrium. That's when you're going to solve for delta Rg. So before you're done, you're still going to need to know this value, and you don't know it yet. But you can solve this by at equilibrium when this is 0 and this is 10.
Got it.
Got questions? Anything good? What's up? So once you've got delta Rg naught, that's going to be the same because we're at the same temperature. But now what has changed is we're no longer at equilibrium because I've given you some partial pressures. So you can actually solve for Q. Now you know delta Rg naught, you know RT, you know Q, you can solve for delta Rg. Yeah.
So we have this, we're solving for this.
Yep, in the first part.
Can we or can't we use K equals 10 or do we use the partial pressures to find?
So the question has 2 parts. The first one says, if it was under equilibrium, K equals 10, and so you can solve for delta Rg, Rg naught.
Okay.
But then, delta Rg naught doesn't change because you're at the same temperature. So even though K is now no longer 10, it's going to be Q that you calculate. You can use the same value for this and you can solve for what delta Rg is. Correct. Just until you get delta Rg. And then it's no longer 10, it's whatever it's equal to. Cool? Yeah. Yeah.
At equilibrium, you just plug in this T right there.
Yep, still at the same temperature. Yeah, this is all happening at the same temperature. We're just changing the equilibrium gases. In one case, they're such that K equals 10. And in the second case, they're going to be something that's not 10. Right? In the second case, Q, yeah, you've got it right. And it's 500, right? So at first, when K equals 10, you're going to solve for delta Rg naught. And then that's the same value. Yeah, then you just reintroduce Q. Remind me your name?
Derek.
Derek. Okay.
So we solved it, but we
Okay.
didn't meet the partial pressures.
Oh, then maybe something's wrong.
Yes.
Where's your work?
Likely. Well, I just plugged
Okay.
in everything in here.
Delta Rg naught is not equal to 0. Delta Rg is equal to 0 at equilibrium.
there we go.
Delta Rg naught is a value they're going to have to solve for.
So,
what you do know is at equilibrium, this left-hand side of the equation, delta Rg, that's equal to 0.
okay, so,
Let's actually rewrite your expression.
yep. So this is actually going to be
Naught
Rg naught.
plus RT natural log Q.
Yep.
So this Q needs to be, we have to solve for this Q because the Q is such a relative.
Yeah, if you actually plug in the values for Q, it's not 10. That tells you that under those partial pressure conditions, you're not at equilibrium. And therefore, something's gonna happen. It's either gonna go forward or backwards to solve Q, and use K to figure out what delta Rg naught is. Delta Rg naught doesn't change. That's the theory part of it. It doesn't care what's happening in the reaction. It's just the theory part. Now, yeah. So you plug in K first, and then, yeah, you set delta Rg equal to 0, and you get a number that I don't actually remember what it is. That's probably right. We're going to work out in a minute. That seems reasonable, though, and that's in joules per mole. That's in joules per mole.
We generally do G naught in kilojoules, right?
Yeah.
It's such a smaller number.
Now this, I thought somebody else had 500 instead of 0.05. I don't know if they were right or you're right, but double check your numbers here, make sure that's right. But this is at least the right approach. Yeah.
On that delta Rg naught,
Okay.
is that little knot up there, that top little circle? Is that, I thought, did you say
Yeah, but that is how they write it, even at other temperatures. What I should have written, the correct way to write it, is I should have put a subscript 960, meaning this is all happening at that same temperature. It's a different value at every temperature. So to be complete, I should have written 960 there. Maybe I'll write that real quick. They have to have something there to differentiate that from the one on the left-hand side of the equation, and they use the not symbol. But you're right. Technically, that's totally different at different temperatures, so you're absolutely right.
So we're saying both is 960.
Yeah, it's all happening at the same temperature. Ian, how can I help? Kilojoules. Yeah, well, it depends on what your gas constant is. That gas constant is in joules per mole. So if you use that one, then you're going to get an answer in joules. So you need to divide by 1,000. Okay, like 2 more minutes and we're going to close the poll on this one and work it out together. Yeah.
Once is it paused? Is it
Oh, I gotta hit play. Let me do that. No, it's okay. I think that you should be able to answer. Yeah. No, just, I'll make an announcement. So you're going to put your answer in just a number. The number needs to be in kilojoules per mole, but don't actually type like kJ or anything. Just give me the number. I don't know what would happen if you typed kJ. I think it would not work because it's only numeric response on this one. Did you put in kJ? Oh, maybe redo it. You can change your answer. Okay, 1 more minute. Get your answers in. Phone a friend if you need to. Is it Nathan? Yeah.
So I found this. So what do I do?
So first thing you do is add equilibrium. When k equals 10, then you can set this equal to 0. And this is now k, not q, because it's at equilibrium.
Okay.
So that allows you to solve for delta Rg naught.
Okay.
Once you solve for delta Rg naught, which looks like you tried to solve for it here. Is that the right answer though? I don't know if that's the right answer, but this looks correct. Oh, no, yeah, it looks correct. I think that might be a math error though. But anyways, once you've got this, then the next step is that's the same number that goes up here. Now for Q, I've given you the partial pressures, so you can actually plug in and solve what Q is and solve for delta Rg, because you'll know everything at that point. So you just solve for delta Rg.
What is Q then? So what
Products over reactants, you take the partial pressures raised to their coefficient. So product is SO3, so it's going to be the partial pressure of SO3 squared, because it's got a 2, divided by the partial pressure of oxygen, multiplied by the partial pressure of SO2 squared.
okay.
So give that a run. We're probably going to close the poll, but give it a shot real quick. Okay, we're going to wrap this one up, get your final answers in, and then we'll work it out together. Okay, I'm closing the poll. Okay. People think what, by the way? So many answers. All of the answers. That's remarkable. Okay, let's work through this one together. Seems like it might be a helpful exercise. Okay, so the first thing to realize on a question like this, the first thing to realize is I've given you not enough information to solve it at first, right? Because I asked you to solve for delta Rg, And I've told you information to solve Q, but I didn't tell you what delta Rg naught is. But I threw in one little caveat here. I said at equilibrium, you know what K is. So if you know that K at equilibrium is equal to 10, that tells you that delta Rg naught is equal to 0. So right away you can say, okay, we have 0 equal, let me change the thickness of this. We've got 0 equals delta Rg naught, which we don't know yet, plus 8.314 joules per mole Kelvin multiplied by 960 Kelvin multiplied by the natural log of K, which is 10. So here we know everything except for delta Rg naught. So what is delta Rg naught? I think I saw, well, let's just work it out real quick. Delta Rg naught is equal to negative 1.8, what now?
18378.28.
Let's just do that, joules per mole. Did people get that same number for delta Rg naught? Thumbs up? Okay, thumbs up. So we're good so far. So now we can solve the second half of this question. And the second half says we're not at equilibrium anymore, right? And the reason that we know we're not at equilibrium is by calculating Q. Q is going to be the products over reactants. So it's going to be the partial pressure of SO3. That's going to be squared. And the reason it's squared is because we have 2 as a coefficient. This is going to be divided by the partial pressure of SO2. That's going to be squared as well, multiplied by the partial pressure of O2. When we plug these in, I'm going to move it down. Check this out. With the magic of modern technology, I'm going to move this down there. It's magical. Okay, we can go ahead and plug these in. SO3 is 1e to the negative 4. That's squared, divided by 0.2, divided by 1e to the negative 3. What number do we get for that? 0.05, I think that might have been it. 0.05? 0.05. So double check the math on that if that came out wrong. So now we know Q, and 0.05 is not equal to 10, so we know that we must no longer be at equilibrium, right? They said at equilibrium K is 10. And since K is not equal to Q, we're not at equilibrium. So now the final part of this question is, okay, which way are we going to go? And we say delta Rg is equal to negative 18378 joules per mole plus 8.314 joules per mole Kelvin multiplied by 960 Kelvin multiplied by the natural log of 0.05. And this comes out to what? Negative 14? 42.9? Just Ashton. Is that kilojoules? Okay, right answer, yay, nay? Most people getting that? I'll double check this when I finish my solutions tonight when I post this online. Any questions on this approach? Yeah. Okay, his question was this. When we figured out Q, its products over reactants, why do we multiply them together? That's the rule. You multiply them together. Okay? We did the same thing with free energy, right? They're multiplied together. Now, if one of these was a solid or a liquid, then they become one and you ignore it. But since all three of these were gases, we need to know their partial pressure and they just multiply together. Okay? We're not going to, for the sake of time in this class, because it's already like a stretch to cover this stuff, we're not going to go into more detail on that. Other questions I can answer on this one? Let's do another one. By the way, when I write these into Top Hat, I give it a pretty generous range. So if you didn't get this exact value, but you got, say, 40 up to 45, I probably would have given you credit. I don't know exactly what I coded, but it'd be something like that. Okay, how about this one? This one's tricky. It says a galvanic cell is set up with zinc metal on one side, and it's got a concentration of 1 molar. And then you've got zinc metal on the other side at a different concentration, right? So in other words, you've got zinc, 2 plus 2 electrons, form zinc metal, and this has some voltage associated with it. And we set that up on both sides, so whatever that voltage is, when we write the opposite, the oxidation reaction, it's going to be the exact same, just negative, such that when we add these two things together, they just cancel out, right? So then it says, at room temperature, what voltage, if any, is produced? So it might be tempting to say, oh great, these things just add up to 0, so there's 0 voltage. But that's forgetting the experimental part, right? So the cell potential, delta V, is equal to the overall cell potential, delta V naught, again, terrible name, delta, overall cell potential, minus RT over NF, natural log of the concentration of our oxidized species divided by our reduced species. Oh, sorry, zinc, not Mn. And when you plug in these different concentrations, you're going to find that you do get a voltage. So give that a shot. I think that's our next clicker question. I think. I'm going to skip that one. Okay, right here. Room temperature is 300 K, 298. Use 300 K and it's fine. Yeah. F, the Faraday constant, is that's coulombs per mole. Okay, basically out of time. So how are we doing on responses? We will pick this one up next time. I think I can reopen it next time, so I'm going to stop it now. But we'll start class with this one so you can get something in. And we'll finish this one. We won't get to the other ones, but there's lots of examples on the YouTube channel if you want to see more examples of this.